Okay, so let's move on to the next session. We'll be talking about existence of the minimum variance unbiased estimator. Okay, so the question arises as to whether a MVU estimator exists, that is an unbiased estimator with minimum variance for all theta. Two possible situations are described in figure 2.3. So 2.3 we have talked about. Okay, so uh, if there are unbiased estimator that exist and variance are shown in A, which is this one, then we say that theta 3 is the MVU estimator. If the situation is in 2.3b, which is this one, some are better than others in some region, but not always, then there exists no MVU estimator. Since this theta 2 is better in that region, while in that region, theta 3 is better. So in the formal case, theta 3 is sometimes referred to as the uniformly minimum variance unbiased estimator, to emphasize that the variance is smallest for all theta. In general, the MVU estimator does not always exist. Okay, so it may be, it may not be. Okay, um, so here we are going to talk about an example, a counterexample to existence of MVU estimator. If the form of the PDF changes with data, then it would be expected that uh, it will be expected that the base estimator would also change with data. Assume that we have two independent observations, theta 0 and x0 and x1, with PDF like this. Okay, so this is assumed, of course, assuming some kind of scenario and then try to solve the problem. So we have x0 distributed by Gaussian as the mean of theta in variance 1. And then x1 is distributed by n of theta. This is Gaussian distribution mean theta and sigma square equal to 1. Or for if theta larger than 0. Or if theta is smaller than 0, then it will be Gaussian distribution with theta and sigma square equal to 2. Okay, so let's see. The two estimators, theta 1, okay. So I think the problem, we look at it one more time. We have observed two theta. One is x0, the other one is x1. And they are distributed, the distribution is used to do the relation, right? Relation. That is used to do the relation. As we said, we have to repetitively emphasize that um, data has to be related to the parameter in some way. Otherwise, the data and parameter estimation wouldn't be able wouldn't be would not make sense at all, because if they don't have relation, then they don't provide information. Okay, so the relation is described this way. So your data relate to mean in this way, and then the next data relate to mean if theta is larger than 0 or if theta is smaller than 0, and relates to that. Okay, so that's the relation, statistical description of the relationship. Then the two estimators, of course, if you have two theta and it relates to the theta as the mean, then the natural selection is you take the average. You take the average. So you do x0 plus x1 and take the average. So this is like an average. And then theta 2 hat is like a weighted average. Right? Weighted average. Weighted average, so it is the x0 uh, 2 divided by 3 plus 1 divided by 3. And then, of course, the coefficients adds up to 1. So they are all good and reasonable. But the thing is, it put more emphasis on x0, 2 over 3. And if you take the expectation, this is equal to theta. You take the expectation. This is equal to theta. As a result, it can easily be shown to be unbiased. Then to compute the variance, we have that. We take the variance. Variance, when you have coefficient, it goes out as square. So square of this is 1/4. Square of this is 4 over 9. And then this is 9 over 1. And they're independent. So the cross term goes to 0. The cross term is 0. So you have something like that. And then let's see. The variance is already given as 1, 1, and 2. So if theta is larger than 0, then 1, 1, right? Larger than 0, it will be 1, 1. So this will be 1. Uh, sorry. Let's see. This will be 1. And then, let me see. This will be 1. So if this is larger than 0, it will be 1 plus 1 divided by 4. That is equal to 18 over 36. The reason that uh, it, 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 it is making the denominator to be 36 is it wants to make it comparable. So it's 1/2 and then making it 18 over 36. And then if smaller than 0, then it will be 1 and 2. Right? So it will be 1 and 2. As a result, it will be 1 plus 2, 3 over 4. 3 over 4. Then it will be 27 over 36. Then if theta is smaller than 0. Okay? And then variance theta 2. If larger than 0, then again it's 1 and 1. As a result, it's 4 plus 1 over 9. So it's 20 over 36 if larger than 0. But if it is smaller than 0, then it will be 1 and 2. So it will be 1 and 2. Then it will be 4 over 4 plus 2. It will be 6 over 9. Then it will be equal to 24 over 36 if smaller than 0. So, okay, so we have calculated. We calculated. And then we try to plot it. The variances are shown in 2.4. 2.4. The illustration of minimum variance unbiased estimator. Okay, so let's see. Between these two estimators, no MBU exists. because if we plot this and plot this on the figure, we see that this is theta 1, theta 2, and theta 1 this way. As a result, you see that theta 2 is better in this region, but in this region, theta 1 is better. So we will say that there's no NVU exists. And it is shown in problem 3.6 that for theta larger than 0, the minimum possible variance of unbiased matter is this, while this is that. Okay, so no single estimator can have a variance uniformly less or equal to the minimum. But the point is, we don't know the value of theta, so we cannot say that theta is in this region. If it's in this region, then we can use theta 2. If theta is in this region, we can use theta 1. But theta is supposed to be unknown. Therefore, we don't know what it is, and we cannot claim any one of them to be better. Okay, so that's the kind of the difficulty if we don't have a uniformly better estimator. Then even if MVU exists, we may not be able to find it. There is no known procedure which will always produce the estimator. But we will discuss several possible approaches. Determine the Kramer-Rao bound and check to see if some estimator satisfies it. Kramer-Rao bound is the lower bound for MSE. It's a lower bound for MSE, which we will talk about later. But we find CRB, this CRLB, and then there is an estimator very close or even matches the CRLB, then we can say that, okay, then this estimator is the MVU, Okay, so another approach including RBLS, but this is very complicated, and we will not discuss this in this chapter. And then or further restrict the class of estimators to not only unbiased but also linear. Linear is making a more constraint, right? Imagine you have a set of estimator, and this could be unbiased, and also there's a class of linear, and then you take the intersection, you will see that it's more limited. But in this region, it's linear and also unbiased, and it makes it easier. But of course, you are more limitations. Okay, so but also linear. Then find a minimum variance estimator within this restricted class. Then approach 1 and 2 may produce MBU, while 3 only if the MBU is linear in the data. It takes maybe a little bit of good luck or coincidence, but again, the estimator is always a design issue rather than something very available. So if it's a design issue, then we have to design it, and design is by itself very complicated. So it takes some procedure to try and see if we can find it. But if we cannot find it, then most likely we need to use other kinds of approach. So the CRLB allows us to determine that for any unbiased estimator, the variance must be greater than or equal to a given value. If an estimator exists whose variance equals the CRB for each value of theta, then it must be the MBU estimator. As I said, If we look at the figure and say, see an estimator that matches this, and then it's an MBU. The the CRLB will immediately yield the estimator. It may happen that no estimator exists whose variance equals the bound, yet an MBU estimate may still exist, as for instance in the case of theta 1 in figure 2.5. Okay, so yeah, it may exist, it may not exist. Then we must resort to other approach like RELS approach, and it finds a sufficient statistic and then use the data efficiently and then finds a function of the sufficient statistic, which is an unbiased estimator. But we may talk about this later. The third approach requires the estimator to be linear, sometimes severe restriction, and choose the best linear estimator. Only for particular data sets can this approach. Particular data, in other words, as I apply here, a good estimator may exist here, or somewhere around here, right? But we are restricting to be unbiased and linear. It's a very big restriction. But if the MBU happens to be in that region, then we will be able to find it by making linearity assumptions. But it may not be always. It may not be always because uh, the a good estimator may not exist in that region. It could exist somewhere else. So only for a particular data, meaning that it's linear. Linear. And can this approach produce the MBU estimator? Okay. And then the next section is tangent to a vector parameter. Vector meaning that we have multiple. We have multiple parameters. And we put it into a vector form. So you have theta 1, theta 2, all the way to theta p. Then if theta, we put it into a vector and then transpose. So it becomes a column vector. So if theta is equal to this, is a vector of unknown parameter. We say that an estimator is unbiased if you take the expectation E theta I hat equal to theta I. And then, of course, there are some prior knowledge or prearranged range for that theta I. But the point is, if you take the expectation, it has to be equal to the true value. If it's equal to the true value, and then by defining E theta equal to, this is element-wise. Element-wise. Expectation of vector equal to element-wise expectation for each element. Then we can equivalently define an unbiased estimator to have the property that expect of this because it's element-wise expectation, and then it's equal to element-wise true value theta 1, theta 2, so on and so forth up to theta p, meaning that the first one equal to the first, the second equal to the second, the third, the p, so that if that sustains, then we call it unbiased. MVU estimate has the additional property that variance is the minimum among all unbiased estimator. So if it has to be minimum among all unbiased estimators. Okay, so yeah, let's stop.